So it's a pleasure to chair this session. So I'm Gang Zhou, professor of computer science from William & Mary. I'm the editor-in-chief for ACM Transactions on Computing for Healthcare. It's great pleasure that the journal and the conference, we can have some deep collaboration. One way is that we have a session for the journal. So any paper accepted by the journal, so you still have a chance to social with scholars in the community. So every year, starting from last year, we have a session from the conference that authors from journal come here to present. And also this year, I also bring the journal editorial board to be together with the conference. So we have more chance to, for scholars to talk together. For this morning, we have 5 papers from the journal. Authors will come to present. We have 75 minutes, so it's up to 15 minutes per paper, including question and answers. So I think the slides are preloaded. I will go with the order on the program. The first one, presenter will be Jinping Li. So the paper's title is Large Language Model-Based Conversational AI Therapist for Daily Functioning Screening and Psychotherapeutic Intervention for Early Smart Devices. That's quite a mouthful. Jinping, oh, okay, good.
How should I, so should I just connect to my own computer?
Have you ever upload? I think you have upload.
Okay, I'm not sure how to, didn't get any. Yeah, I was told using my own computer, but I'm not sure how it goes. How do I switch them? Okay, great, thank you. All right, sorry for the little bit technical issue. So hello everyone, I'm Jinping. I just received my PhD from Columbia University under supervision of Professor Xiaofan Zheng and Professor Matthias Prindle. And I'm honored to be here to present our work. Oh, and by the way, I'm joining UNC Chapel Hill as assistant professor next week. So yeah, I'm looking for collaborations as well as potential PhD students, as postdoc students. Yeah, so feel free to reach out, yeah. I'm honored to be here to present our works at ACM CHASE today. And this work is in collaborated with licensed psychotherapists Vera Shao, as well as Yuan Qijia and Hao Xuan. So despite the global efforts to improve healthcare, there remains a shortage of medical professionals, and this color-coded world map illustrates the distribution of medical doctors per 1,000 people worldwide. So while some countries have relatively higher doctor to patients ratio, so the overall number are still not optimal. And this bar plot shows the number of mental health workers per 100,000 people, which means that the global shortage of mental health workers is even more severe. Survey has shown that the number of IoT connected devices grows rapidly recently. These connected devices, right, including wearables, home assistant devices like your smart speakers, smart home systems, play important roles in people's everyday life and enable pervasive healthcare and mental wellness support for everyone. In the fields of human-centered AI, ubiquitous and mobile computing, and digital health, researchers are actively looking into different approaches to enhance the mental health care. And the key research matrix, including, for example, emotion states, vital signs and biomarkers, human activity recognition, social interaction, and other interaction and intervention. This matrix typically rely on inputs such as biometrics, ambient intelligence, as well as speech and conversation. For example, researchers investigating using radio frequency to detect 4 emotion states and 10 classes of human activities. And also explore using heartbeat modulated ultrasound echo in the ear canal from active noise cancellation headphones to detect heart rate and heart rate variability. Researchers also leverage channel state information from Wi-Fi to detect human dynamics. And also folks from UWatch have come up with a conversational mobile web app to support the dialectical behavioral therapy practices. But this work was majorly focusing on the psychotherapeutic practices and only handled close-ended response. So as you can feel, only a few research in our field actually connect this matrix to mental health screening and provide psychotherapies to support mental wellness. So how do medical health experts, right, the domain experts do to assess the mental wellness? Traditionally, they screen using screening tools such as mental status examination, adult ADHD self-report scale, PHQ-9 for depression, and GAD-7 for anxiety. This screening usually conducted by licensed professionals, which is a barrier for low-income and remote area people. And then back in 2020, I had a chance to talk to a licensed psychotherapist during a Columbia alumni event. She's in the largest mental health counseling institutions in the New York City area. And I came to her and said, hey, we are also working on some mental health related topics, and also introduce the mental health works in our fields to her. And she said, wow, that's cool and helpful for them and good to know. But she also mentioned to me that during their clinical practices, they also care a lot about the dimensions that cannot be directly transformed by those questionnaires, the screening tools they are using, as well as by the matrix we are caring about, right? They chat. For example, instead of a pop-up survey asking, on a scale of 1 to 10, how's your mood today? They might ask more open-ended questions like, how's your relationship with your family members or significant others? And the response from the patients or the clients can be infinitely diverse. So how does a psychotherapist visit usually look like? Therapists brought up that they usually chat about daily life with patients and ask questions to understand day-to-day functioning based on their years of professional experiences, as well as the rubrics in their discipline, such as DSM-5 and DLA-20. And day-to-day functioning is highly correlated with mental health status, and routine monitoring will be helpful. And then they will provide personalized and targeted evidence-based treatments like motivational interviewing and cognitive behavioral therapy. However, currently the barrier to accessing mental health professionals remains very high, and therapists also have limited bandwidth to support continuous monitoring for everyone, even those who already have access to them. And traditional methods highly rely on patient self-reported activities. So I started to think, as Dr. Lim mentioned in the keynote speaking, right? How could we, electrical engineers, biomedical engineers, computer scientists, right, could work with these domain experts to bridge the gap, right? How can we have AI-enhanced smart home solutions that can provide pervasive and accessible, acting as an AI therapist to provide continuous, comprehensive, and subjective screening, and to deliver effective psychotherapies in a privacy-aware manner. But one key challenge along the way is that therapists, there's a little culture shock, Therapists can ask infinite many questions, and their clinical procedure is not something that machines can directly take actions on. So in order to actually take advantages of AI and digital health stuff in our field, right, we spent several weeks interviewing more than 10 therapists and collaborated with them to come up with comprehensive and effective representations of clinical procedure to some machine-readable and actionable formats. And we actually came up with 37 dimensions to screen the day-to-day functioning and infer the mental health status. And we define the scores for each dimension. So 0 for doing well, 1 for some issues but nothing urgent, 2 for cases that need attention from healthcare providers. And we also define the rubrics to give this score in each dimension. There are also other design requirements brought up by the therapists, including minimum lifestyle disruption, privacy awareness, as well as accessibility. So for the preliminary stage of our study, we're trying to screen the 37 dimension and provide psychotherapies in a more pervasive and non-contact way. So we leverage speech and conversation. And to bring our vision to practice, we built Katie, collaborated with a therapist, which is a conversational AI therapist that screens and accesses the day-to-day functioning of the occupant across the 37 dimensions and provides appropriate psychotherapeutic intervention and empathic validations depending on the physical and mental status of the occupant. And to enable nature and seamlessly interaction, Kitty integrates with like smart home ecosystems like your Amazon Alexa, as well as leverage like customized Flutter-based platforms so people can access from their mobile phone or like computer to deliver all these conversational functions. We implemented a proof of concept prototype of Kitty and conducted studies over 14 days and 24 weeks, which include both in-lab and at-home sessions. And therapists also provide bi-weekly check-in to ensure the validity of the study. Now, let me introduce more in detail. To mimic what real therapists do, Kitty uses a recommender system based on reinforcement learning with Q-table to decide the way to drive the conversation. And in particular, Kitty takes the action AT to select which dimension to ask at the current state. Specifically, therapists usually start their treatment by following up with a dimension that specific clients doesn't do well before, or they will sort of based on their professional experiences to say what's the dimension that general public might have issues on. So to enable Kitty understand and reason, we're also using a large language model-based response analyzer to check if the user answered the question, classify the response into the 37 dimensions, assign a score, like 3 score categories to it, and the weighted score is used as a reward to update the Q table, and the weight is empirically set by the therapist. And this updated Q table will use as a reference to guide the next conversational session. And if the user needs further attention in the response in the current state, when the score equals to 2, Kitty will ask follow-up questions and provide psychotherapeutic conversational intervention, which including motivational interviewing, MI, and cognitive behavioral therapy, CBT. And we designed quality control logic flow to, with the licensed therapist to lead the user through the conversational psychotherapist efficiently. And in particular, collaborated with them, we incorporate the MI techniques in what they call reflection validation process. And the large language model-based RV reasoner, validator, and guide are implemented to ensure the effectiveness. So how does them actually fit in the conversational flow, right? Let me give you a short example over here. So at the current state in dimension N, Kitty asks, have your weight changed significantly recently? The user answers, my weight increased a lot. Response analyzer will classify the response to dimension N and assign a score of 2, and start the reflection validation process with the MI techniques. So in particular, Kitty will ask the user to tell more about what's going on. And RV reasoner will check if the follow-up response is valid or not. If it is valid and within the current conversation topic, RV validator will provide empathic validation and provide consolation to the user to say, okay, what's the suggestions and what's like the better coping skills if you do stress eating. However, if the follow-up response from the user is not valid, for example, here, the user said, I'm an ISFP, which seems to be irrelevant to the weight change. Then the RV guide will try to guide the user to tell more about what's going on within their topic that are relevant like in the current state. So to design and select the best at that moment, based large language models for response analyzer, we did like micro benchmarking with a data set provided by the psychotherapist, which includes 305 classes general responses to express like the yes or no, maybe, and question stop, and 7,000 dimension score segments from 6,950 response in the 37 dimensions. And according to our micro benchmarking results, the fine-tuned GPT 3.5 Turbo gave us the best results and thus selected for the final implementations during our human subject experiments in the 14 days and 24 weeks. And there are 454 conversation sessions with around 18,000 and 2,000 segments of subjects' responses to Kitty's original questions and follow-up questions from like the human subject studies. And therapists helped us annotate all the Kitty's system response during our experiment, by the way. And we saw that Kitty hits an impressive 97.6 accuracy in classifying the user response into 37 dimensions, and also achieving over 99% accuracy in classifying them into the right score category. And plus, we also did macro benchmarking for the RV Reasoner, Validator, and Guide, and select the prompt GPT-4 for RV Reasoner while having the prompt-based GPT 3.5 Turbo for RV Guide and Validator based on the system performance. We can also see that during the human subject study in our experiments, Kitty, RV Reasoner, Validator, and Guide performed exceptionally well as well. So now let me move to the CBT process, which usually includes 3 stages. And in the actual psychotherapist visit, this usually happen at the end of the conversation session. The 3 stages usually include recognize the negative thoughts, challenge negative thoughts, and reframe the thoughts. Similarly, we have CBT questionnaire to lead the conversation, reasoner to validate if the user follow the conversation, and a guide for each of these 3 stages to ensure the validity of the CBT process. As the 3 stages of the CBT has different focuses, so each stage have its own questionnaire, reasoner, and guide to control the conversation quality. So for the micro-benchmarking purposes, therapists also provide us with 146 example situations within the 37 dimensions and the 3-stage CBT responses for each of these situations. And based on the model performance, we selected prompt GPT-4 for all the reasoners in the 3 stages and of CBT. And in addition, in the 146 example situations, there are 5, 17, and 33 responses that are invalid and needs guides in CBT stage 1, 2, 3. And we select a prompt-based GPT 3.5 turbo for all guides in the 3 stages of CBT. So with our therapists, again, annotating each of the KD's response during the experiment, we can see that KD successfully reasoning the validity and the utility of the user response and effectively guide the user through the CBT process. Last but not the least, we're open sourcing the micro-benchmark data set, but not the actual human subject data set data because of the HIPAA issue, but the data set provided by the therapist, we're open sourcing it. The therapists also provide clinical evaluations on KD. The Wilkinson single-rank test for the 14-day study found a statistically significant decrease in the concerning dimensions for the 20 subjects. And for the 24-week study, therapists observed improvements in anxiety, depression, and functional difficulties. So to summarize, KD provides comprehensive screening, delivers effective psychotherapeutic interventions, and is clinically validated. And also currently, our lab is working on upgrade KD to connected home AI therapist. In addition to conversation, the new KD also take advantages of the smart home sensors to screen the 37 dimensions and using home robot to interact and conduct precautionary check-in with the clients and occupants if like any abnormal behavior is detected. All right, thank you, and I'm happy to answer any questions.
Let's be creative. We're already behind time. How about this? All the presenters, please stay until the end of the session. We can ask questions probably together. Let's say everybody, the 5 talks, let's finish the 5 talks first. Then probably there are some common questions, we can save some time. Hopefully we don't push back the schedule too much. Okay, next one is Xiaoyu Chen. The title will be Adaptively Weighted Top-End Recommendation for Organ Matching.
Doesn't work. So. All right, I will not delay too much. And my name is Xiaoyu Chen. Call me Xiaoyu or Chen, doesn't really matter for me, unless there's another Chen here. I'm assistant professor from University of Buffalo, and this is the joint work with my former PhD advisor, Dr. Jing Ran, and my friend Parshing, and they cannot be here, so I'm representing them to present. And I cannot promise you I can answer all of your questions, but I'll try my best and forward the question to the proper person. In today's talk, we will be presenting the adaptively weighted top-end recommendation for organ matching. And if time allows, I also present my favorite work independent down based on the distribution in distribution out regression, that is a linear regression model taking distributions directed as input and output. So this is more statistical flavor. So this problem is really motivated by the kidney shortage for transplantation. In case you don't know, this is data from kidneydonation.gov website. In 2018, around 93,000 people, they need kidney to be transplanted. They're waiting on the list. But only 16,000 are donated from the live donors. So this is a huge gap that one wants to reduce, right? So there are, of course, multiple ways to reduce such gap. The first way is, of course, to pursue more generous people to donate their kidney. But imagine that if you are the generous people, what are the concerns in your mind? You may have many concerns because you only got 2 kidneys, right, left and right. If you donate one, what will be the impact to your health, to your finance, and to many things in your daily life? So this is the roadmap that's shown by UNOS, which is the organization that in charge of all the organ transplantation in the United States. It's a long route. The route split between 2. One is the patient who needs the organ, and one is the living donor who wants to donate their organ. And after a lot of education in the process, which usually take years, they will eventually be paired together. But that pair is tricky, right? For example, thinking this way, when a kidney is taken out from the donor, you can assess kidney by using biopsy or other type of techniques. And these characteristics should be well matched with the patient to ensure the post-transplantation performance. But how could that happen? Currently, people at UNOS, they created a score called KAS. It's a kidney allocation score. That KAS in general is a linear regression. Everyone in this room are familiar with linear regression. It's more empirically done. And then this is something running behind the organ transplantation. The OPTN, the Organ Procurement and Transplantation Network, serves as the central role that in charge of the donation, the patient waiting list, and transplantation centers. It's managed by UNOS, and OPTN will list all the patients on the waiting list in their list, and then they have 90,000 patients on the list yearly. And OPTN coordinates with the organ procurement organizations called OPOs. These organizations contact the potential donors and persuade them to provide their kidneys, and usually their family members of the patient. The provided kidneys will be transferred to the transplantation centers, which will perform the transplantation for the patients. So that's the general thing. And we really identified one key research gap here. That is, how can we better match the patient with the organ? That should ensure the post-transplantation performance, even though the transplantation performance can only be measured afterwards, right? So that's the gap. And the objective is, of course, to allocate the limited viable organs to the most suitable patients, right? So that we do not want to waste the organs, but want to ensure the post-transplantation performance. If the matching is ineffective, then it directly leads to the unsatisfied post-transplantation matching performance that will harm the health of the patient who are on the waiting list, and in turn, it will waste the organ. An organ, once it's been taken out from the human body, it can not last long. So inefficient matching may waste the organ because the viability dropping over time. The challenge we have is current organ matching decisions were making by the algorithmic scoring models based on linear regression, which is more empirical. We want to improve that part. We assume that the similar post-transplant matching performance come from the similar organs or similar patients. That means we assume that, yes, we can organize such a waiting list versus organs as a matrix. Each row in the matrix represents one organ, and each column in the matrix represents one patient. You can imagine how sparse this matrix is, right? So if you look at this graph showing here, it's highly sparse because you can only observe one score as the post-transplantation performance for one row, because one kidney can only be transplanted to one person. So we developed an algorithm based on linear regression and matrix completion by assuming that the actual post-transplantation performance is linearly associated with the covariates of the patient and the covariates of the donor. That's represented in X. And then we also assume that there are some hidden information in Y, that because we found that error term is no longer IID, right? This will harm the linear regression model. So we assume that such hidden relationship between different organs and between different patients can be represented in a low-rank matrix R. In this way, we reorganize the linear regression model by regressing Y not only on X, which is a standard linear regression model that UNOS is using. Instead, we also mine more information from the error to make the E, the actual error, IID. So this is related to one algorithm we proposed in the paper. That is the adaptive weighted linear regression model. So in this adaptively weighted linear regression model, we want to minimize the least square, regularize the least square loss based not only on the difference between Y and X beta or R, but also on weighted difference. And this weight is computed based on a softmax so that the total weight will be automatically enforced to be 1. We use a simulation study to evaluate it because in 2020, we asked UNOS for real data, but they asked us to prove your concept first. And this is a proof of concept. They gave us some key distributions of the characteristics between patient and donor. We generate some fake data based on this. And in addition, they gave us the KAS score that's based on a linear regression model, regressing KAS, the kidney allocation score, on top of the life year from transplantation, LYFT, the kidney donor profile index, dialysis time, and the calculated panel reactive antibodies. And based on this data, we started to evaluate the performance for 2 performance metrics. The first one is called hit rate. That means we want to ensure our predicted top-ranked patient for one organ match the actual top-ranked patients for one organ. How could we build that match is evaluated based on the hit rate. Secondly, in addition to the matching or not, we also want to investigate what's the order of our predicted versus the actual order of the performance. So we use this NDCG, which is called normalized discounted cumulative gain. So the difference between hit rate and NDCG is that hit rate does not consider the order or the actual ranking of the patients in the system, but NDCG considers the rank. So here's the comparison results. We compared with 7 benchmarks, including neural networks like neural collaborative filtering and deep factorization machine. And the red line shows our proposed model is always on top of the other benchmark models, except for the NCF, because NCF really did well in this 200 organ, 1,000 patient simulation study. And if we reduce the number of organs to 20 in the matrix, then our model still work well when the matrix is pretty sparse. For example, 99% entries are missing. And similar situation happened for the NDCG. Again, NDCG measures the ranking accuracy of the proposed model. All right? So in summary, the objective of the kidney matching problem is to allocate the limited viable kidney to the most suitable patients. And the proposed model, AWTR, it significantly improves the top-end matching performance between donors and patients in a simulation study. And this really attracted me to think more and dig deeper into the operation room. In the operation room, this is a typical setup. The physicians are facing with too many monitors. They have to make very accurate decisions. For example, when to use what medication to control what wearable. during the system, during the surgery. So this really motivated me to think of how to facilitate better decision-making process. Instead of organizing the data into time series or functional data, we consider to organize the data by defining one sample as multiple input distributions and one output distribution. This contrasts the traditional linear regression model or functional regression model, which takes the scalar values or functional values as input and output and other functional values or Euclidean data. So in short, we call the original, the conventional statistical model as the statistical models working in the either Euclidean space or function space. But now we're interested in the empirical distributions that really locates in a smooth manifold. And this manifold has been well known since the proposal of diffusion models. Because we now know that these empirical distributions, if we assume they are probability distributions, like histograms, they locate in the 2 versus line space, which is a pseudo-Riemannian manifold. Then the difficulty thing is, how can we define the addition and scalar multiplication to establish the linear additive structure between distributions? Without that, we cannot establish any linear regression model. But recall our motivation is we want to assign a linear regression coefficients like alpha to each distribution value samples. How can we do that? We propose to have a revisit of the linear regression model in Euclidean space. For example, we are used to y equals to ax plus b. That's a simple linear regression model. But what if we consider the simple linear regression model in a different way? If we consider the deviation between yi and y bar, which is the average of y, equals to beta, which is scaling factor or slope, multiplied with the deviation between xi from x bar, the mean of x bar. Then this becomes a new formulation of linear regression model. It's still simple linear regression model, but then we can model the deviation directly instead of modeling the actual observation directly. This enabled us to think maybe multiple linear regression model in Euclidean space is just by sequentially adding new scaled deviations to the average of the response, y bar. This observation really allows us to construct a linear regression model or multiple linear regression model in 2 versus line space based on the manifold structure or differential structure. And this allows us to create a new type of regression model on manifold. It's called distribution in, distribution out regression, which is a multiple linear regression that takes distributions as input and output as another distributions. I apologize, this should be a GIF. You should see animations here, but it doesn't display here. But if you look at this chart, the horizontal axis is the cardiac output, which is a random variable. And the vertical axis is the density of this random variable. We use different lines to represent different distributions. We're starting from the so-called Berry center, will average the distribution across different patients in the population. And starting from there, which is y bar, we keep adding new predictors to it, skewed by linear model coefficients. We found that ultimately we obtained a prediction in a blue line representing the distribution, while the actual distribution is in red dotted line, and they match together. Especially, this patient has a coronary heart disease, and the rhythm of their heart was broken. So the dual model distribution can be well predicted by the proposed model. And also, we found that the model coefficient alpha can be used to indicate the relative importance of the predictor. This is just like the linear regression model, because we proved that this model is best linear and best estimator in the 2 versus 1 space. All right, and thank you so much for listening, and thank you for inviting.
Okay, thank you. Next speaker, please come up. So next one is MedInsight, a multi-source context augmentation framework for generating patient-centric medical responses using large language models. Presenter will Sebastian Napan.
Good morning, everybody. My name is Subhas Nepane. I'm from Mississippi State University. I'm a PhD candidate. And today I'll be talking about our work, MedInsight, which is a multi-source context augmentation framework for generating patient-centric medical responses using large language models. So briefly going through the agenda for this presentation, first I'll introduce what this topic is, our motivation as to why we need this kind of systems, and briefly go about what are question and answering systems. Then we'll talk about current research gaps in question and answering systems in healthcare related projects, the architecture of MedInsight, and then we'll discuss some results, and then finally conclude with key takeaways from this presentation and our future work. So healthcare ecosystem is non-linear interaction between different kind of stakeholders, starting from patient, providers, and medical institutions that do research on healthcare. So the primary or the central figure of this healthcare ecosystem is patient, of course. It can be you and I or the doctor itself. So your primary care providers are your first point of contact, and then your secondary care specialists are your advanced care provider who actually provides you specialized service, and academic medical centers are the institution who actually does research on healthcare, right? So, and there are like a lot of technological component that is involved in this ecosystem. It can be AI, it can be other systems, for example, Epic, Cerner, those are the system, healthcare management systems, so on and so forth. So a lot of this healthcare ecosystem, in this ecosystem, the central figure is a patient that we just saw, and they face a lot of issues. So patient itself, they are not as adept in technical medical terminology as their doctors, right? For example, how many times we go to doctor and remember what was prescribed to us, what was our medication? I don't think most of us remember what kind of conversation we had with our provider when we visited them in the last time, right? So one of the issue is, again, the patient understanding the medical terminology, and research at Mayo Clinic, who I also worked with, I would say, suggests that some of the issue is listing medication, understanding the purpose of that medication that was prescribed for some kind of condition to the patient, and also stating side effect, right? So all of these issues of or let's say impact of poor comprehension about understanding their medical history or some medication leads to certain issues. For example, cost to healthcare. Of course, if you cannot interpret what was discussed, and if you cannot adhere to medication, then there is like high cost to healthcare, and it is estimated the cost of healthcare in the United States alone annually is around 300 million a year or more. So another issue is patient confusion, of course, non-adherence to medication and misinterpretation. So addressing these gaps or addressing patient comprehension requires, or research, what they suggest is that patient comprehension is really crucial for addressing healthcare quality. And there are like pressing need to for a system which can bridge this communication gap between patient and healthcare provider. So one of the ways to do is to kind of like start looking into leverage generative AI and different kind of AI technology and make context over AI frameworks which can do a bunch of things for us. For example, it can provide us personalized, targeted medical recommendation. It can also make some clinical decision support system, or there should be. We'll talk more about what this context awareness and context augmentation is in the later slide, but also it can also help in automation of documentation. So briefly going through what question and answering system, as a simple concept, question and answering system can be viewed as a computational model where you have a query, you have a knowledge base, and you have a mapping function which is going to use your neural or deep learning model to use your input question in natural language and use that knowledge base to generate an abstractive answer for you. So there are different kind of architectures out there in market. So all of us are familiar with one example, ChatGPT, which is generator-based model. So you pose a question to ChatGPT and it will generate some answer to you. And there are other frameworks or other architectures out there, such as retriever generator model, or you can also say this is kind of like a RAG. So you have a retriever where you ingest external knowledge to your retriever, and then you use that as your context and pass it to a generator, which is going to generate an answer for you, and which is usually an abstractive answer. So now we saw like traditional, question and answering system, which has only one knowledge base, or one knowledge base. And now next generation medical question and answering system should not just only have one knowledge base, but these question and answering systems should be very personalized. It should understand a patient's context and give you a very targeted response. Right. For example, in this example on your left-hand side, we see a patient, a 42-year-old, white female, presents a complete physical and follow-up on asthma. And if she is asking questions such as, what are the potential triggers for worsening asthma, and how can I minimize exposure? So basically, this question is very personal. So if she were to ask this question to out-of-the-box model, in any given, ChatGPT or Perplexity, those kind of, systems, then she wouldn't be able to. She will get answer for sure. It might hallucinate. It might not give you a very personalized response, because you see these frameworks wouldn't understand or wouldn't know the history of that patient, right? So next generation, of course, the objective of this next generation medical question and answering system should be very contextual, again, targeted, and then it should provide you personalized answer. So in the research domain, so there are a few works that has been done to address this issue, but all of this work, what they use is like they only use one single source to answer any question that is related to patient. But however, our work doesn't just use one source, it includes three sources. So one is being your patient history, medical history itself. Another is that we use medical or authoritative textbook, which is coming from the medical literature. And then third is the clinical guidelines. For example, if I'm asking something about asthma, then I should be able to know what are the clinical guidelines. If I'm asking certain doses or ways to administer some medication, if there is interaction between, if I have a history of taking multiple medication, then I should be able to know that, how should I administer that, and what are the current guidelines as to how do I do that. Right. So of course, the issues in the healthcare itself is, the data itself is fragmented. So there are like multiple, data silos, and it is very hard to integrate all these sources together. So what we propose is we kind of like create an augmentation framework, which is going to combine all these different kind of knowledge so that it will be helpful for us to generate this contextual answer. And of course, if you are using language model, it has like inherent challenges. For example, hallucination is one of them, context blindness, and also knowledge cutoff. So we know that language models are trained on corpus of data, that is their parametric memory, and then if we were to just rely on this pre-trained model, then it won't be able to give you updated knowledge, right? So that's one of the things. So all of these would actually lead to impersonal care delivery. That means patient receive one-size-fits-all advice, leading to, again, mistrust and suboptimal outcomes. And why this matters is, again, for key things. One is your patient safety, healthcare efficiency, and equity. So since we will be talking more about context, so context can be viewed as any information that can be used to characterize situation of an entity. An entity is a person, place, or object that is considered relevant to interaction between user and application, including the user and application themselves, right? So building upon this definition given by the authors, how we define our patient context is a comprehensive set of information and factors that is related to individual patient. So we map this patient context with their medical history. FH is your family history, social history, medication, demography, living conditions, and treatment plans. So that's our patient context. And then how we map this patient context to our previous example that we saw for that 42-year-old lady is that her context would be demography, of course. She is like 42-year-old white female. Her medical history includes asthma, allergic rhinitis, and other stuff. So M, again, of course, medications and family history, social history, so on and so forth. This is how we map. And then in this work, we introduce a concept called context augmentation. Now we understood that what context is now. Now look at how we kind of like bring in all different kind of knowledge together. So context augmentation is a technique of integrating patient context that we saw earlier with factual medical knowledge and clinical guidelines from web sources and that are trusted. For example, clinical guideline could be your Mayo Clinic or WebMD or CDC guideline, and factual medical knowledge means the medical textbook in itself. So we combine these together as a union function and then create this augmented context or AC, and the whole process is we call them context augmentation. So really the objective here is to investigate, the impact of augmenting unstructured doctor-patient conversations with, factual medical knowledge and language, on language models' ability to provide accurate and contextually relevant answer to medical question, right? So the mapping function that we saw earlier, remember we had this M as it can be neural, computational model. It can be language model or deep learning model. And we had this question, which is like natural language question. And then we only had a KB, right? So now we convert that KB and then include this, patient context, authoritative medical guidelines, and web guidelines, and then create this augmented context to generate abstractive answers. So in this KB, we do context grounding so that your answer becomes very contextual and relevant to the particular query. And of course, the outcome for this kind of mapping is holistic patient-centric answer grounded in context, accuracy, and relevancy. So let's look briefly on the architecture that we developed. So MedInsight has like three phases. One is your patient context retrieval, which is the first part, and the second part is medical knowledge retrieval, and of course, third part is response generation. So the patient context retrieval is retrieving the patient history, medication, so on and so forth. And then the second phase is like kind of like retrieving all the related knowledge to about that history using the two things. One is your medical textbook and another is your web platforms. And combining all these, and then what we do is we bring all these three together and pass it as a context to our generator, kind of like the double-sorted like a rack pipeline architecture here. So that will be passed to our controller LLM, which is going to generate a contextual, targeted, and personalized response. So looks a little bit distorted, but these are some examples of how it looks actually in real life. Like, for example, this is your patient-doctor conversation. What we do is we do like convert that conversation into kind of like medical transcript. I don't know if we are familiar with clinical summaries. One of the summary is a SOAP note. Kind of like we convert that conversation into a text blob and then convert that into SOAP kind of summary. Even though it doesn't have like SOAP categories in there, the approach we use is like zero-shot prompting to convert the text blob or conversation into that particular form on the third column over there. And then after that, what we do is we, for example, if we ask question like, how do I use the prescribed EpiPen in case of an emergency? What we need to understand here is this is not just a standalone question, right? So it has the patient unique context, and the model should also always analyze what was in their history before giving answer to them, right? So after all that, we get this contextual answer like this. And for this, since medical history, even if the consult note, physical and therapy note would be like pages long, super long, like every day you can have like at least 10, 15 different kind of progress note, consult note. So one of the problem is to fit all that context into the model, right? So we use a concept called, contextual compression, which will compress the data itself, but it's not going to lose as much of, important factors. So we apply that, and then we get this answer. So data set used for this experiment is empty sample data set. This is publicly available data set, and we use 10 different kind of, medical textbook for this case. And for each of these different scenarios, we are very specific question and examples can be, see how personal question this can be, is like, can you explain the rationale behind adding flovin to my current treatment, and is there potential side effects I should be aware of, right? So to evaluate this pipeline or framework, we look at, two different kind of framework. One is for, of course, for semantic similarity of answer, we look at BERT score, and for lexical, we look at Rouge score. And also, since this is like end-to-end RAG pipeline, we also use Ragos framework to evaluate. At the time, we only had the ability to use two different models, GPT 3.5 and Mistral 7B. We did try with other variants of language model like Llama and Gemma at the time, but they did not perform well. So we had to discard those models. But for Ragos evaluation, one of the things that we really wanted to consider was, since it gave us ability to check if our context itself is good enough or accurate enough or not, we looked at answer similarity, correctness, and context precision itself, and we had like fairly good score with Ragos framework. So of course the score here says like if represents 0 to 1, 0 being your suboptimal score and 1 being your good score. So of course, this is like medical question and answering, right? So it should be subjected to SMEs or subject matter expert who can definitely say whether or not these answers are good enough, because it is like very high stake environment where life and death situation, kind of like life and death situation for patient, right? So we subjected a panel of 4 SMEs. Given the very expensive nature of human assessment, we could only afford 4. And what we do is first we kind of like used a 5-point Likert scale to see if those answers were good enough or not. And out of that we had like 5 categories to see those answers were correct or not. And then the average score we obtained was 4.6 out of 5. And also we wanted to do whether these 4 SMEs were in agreement with each other in providing their response or not, right? So for that, what we did is we did a FLIS multi-rater kappa analysis, and then our overall agreement was around 0.660. This is in a scale of 0 to 100. It's not percentage. So this is fairly, like a moderate, agreement. That means we didn't have perfect agreement because the SMEs that we used had like varying level of experience. Some were like recent resident doctors, and some had like 30 years of experience, right? So their subjectivity of being same thing was different. That's why the score is a little bit low. So the key takeaways from this work is that context augmentation indeed helps improving contextual relevance and answer relevancy, and this in turn makes our response personalized, targeted, and contextually relevant. And in future, what we really wanted to look at is to mitigate biases. I don't know if this can be even possible, because our whole framework is going to be dependent on how well or how unbiased the external sources are. If the medical textbook itself is biased, or clinical guidelines are biased, it might not work. Like the keynote speaker talked about garbage in, garbage out, right? If we are ingesting model with garbage, then of course our response would be garbage out as well. So that's one of the challenges in this kind of work. Of course, we also want to make sure our responses are, trustworthy, and we wanted to use, like some explainability methods, such as, attention visualization, or, even SAP method. And of course, right now, this framework is using only dense retriever, but we also want to see if there is a way we can combine sparse and dense together, because medical jargons are very important, and then we want to preserve the lexical component out of and this kind of responses, so that those keywords are also always present in the answer. So saying so, I would like to conclude my presentation, and thank you so much.
Okay, thank you. We have a lot of pressure to keep in time. Apparently, we don't have enough time, so I would ask a favor for the following speakers, if you can, save us some time. Okay, the next speaker is Eli Hossain. Title is Large Language Models for Opioid-Induced Respiratory Depression Prediction in Hospitalized Patients, retrospective study. Yeah.
Thank you. Hi everyone, I'm Ella Hossaini from University of California, Davis. I'm glad to present our paper, Large Language Model for Opioid-Induced Respiratory Depression Prediction in Hospitalized Patient, a retrospective study. Today I'll go through the background first and motivation and unique challenges in predicting opioid-induced respiratory depression prediction, and then I'm going to introduce LLMs and how it can help us to overcome these challenges. And then I'll walk through our data, methods, and results, and then conclude with the future direction. Opioid-induced respiratory depression, what is this? It's an adverse effect of opioid medication. It's resulting in slow and shallow breathing, and sometimes it's cause complete cessation of breathing. And in many cases, it causes a reduction in oxygen level, which lead to hypoxic and anoxic brain injury and heart injury, and sometimes it can cause permanent damage or even death. Over 50% of patients in hospitals receive opioid, and up to 4.2% of them experiencing opioid-related adverse effect, including ORD. And it's not only clinical adverse effect, it's also can increase the hospital stay by 55% and 47% in cost. And also, it can increase the risk of readmission in readmission in 30 days by 36%. But there are several key challenges in predicting OIRD. First is individual variability. Patient can have a wide range of sensitivity to opioid due to the different risk factors, like age, like their medical condition, sex, gender, and also because of genetics. And the second one is the limitation of continuous respiratory monitoring. Outside of ICU is not feasible, and it's really rare. And many patients in hospital are on non-opioid medication. And sometimes interaction between non-opioid and opioid can cause and amplify opioid effects. And finally, traditional models cannot handle or predict this OIRD because they are going to oversimplify the data and clinical note and cannot find a relationship. So here there is a need for more intelligent approach, which is text-aware approach. So we are going to use LLM, which can interpret unstructured clinical text and also can provide more accurate and personalized risk prediction. AI is transforming healthcare, and they enable innovation solution, and they can uncover pattern in big data set, and also can streamline workflows by automating repetitive tasks. AI technology can also impact on, can improve precision in diagnosis, and also reduce the cost, and also it can provide early intervention, which all of these factors are critical for OIRD. LLMs are a branch of AI, which is very helpful, especially in clinical natural language text. And some of them are specifically designed and trained on clinical data. One of them is BioBird, which is trained on PubMed articles, abstract and full text articles. But Clinical Bird and Gatortron, both of them are trained on actual clinical notes. Clinical Bird on over 40,000 ICU's notes, and also Gatortron is using UF Health, PubMed, and Wikipedia. And all of these models can give us better insight of clinical notes, because they are a specific domain for clinical. Our approach contains three stage. First of them is data collection, which is gathering data from patient from UC Davis Medical Center EMR, and then data processing and feature selection, which we use this structured data from EMR and then generate a narrative, a clinical narrative of that data, and then using GPT for feature selection. And finally, the last stage is training and evaluation. And all of these stages, we use both traditional machine learning and also LLMs to show the added value of using LLM. For data, our data is a retrospective study from UC Davis, collecting data from adults between 2010 to 2020. It's over 2,600 patients EMR data, and over 1,100 of these patients receive naloxone, which is the adversely linked the opioid effects. And 28% of these data labeled as OIRD. We labeled it as, if the naloxone has successful effects, we label it as OIRD. And also we extract key risk factor, including demographic, tobacco use, medical condition like cardiac, lung diseases, and sleep apnea, and also their lab results. This is the distribution of our data set. And for the next step is processing and generating the narrative. We have to convert the structured data to narratives. So we use the rule-based approach to synthesize narrative from those columns, and which each narrative includes demographic, smoking status, medical condition, and lab results. This is an example of our generative narrative. And this, when we feed this into an LLM, it's acting like a doctor to process patients' notes. The next step is feature selection. We wanted to find and identify most informative features because we had over 52 features in this data set. So we wanted to reduce the dimension of our input space. So we first used a statistical analysis like Katz proportional hazard regression model to identify those risk factors, significant of risk factor. But because this model oversimplify the text of these clinical notes, it lead to information loss and also suboptimal performance of model. So we use GPT-4 model to identify these 25 features because GPT-4 can recognize the non-linear relationship and also between variables. So after feature selection, we fine-tuned BioBERT, Clinical BERT, and Betatron on our data set on a binary classification. It's detecting it's ORD or it's not. And we use Hugging Face for implementation. So here are two sets of experiment we conducted. One of them is for traditional machine learning and also large language model. For traditional machine learning model, as I said, we need to simplify the model and categorize it because they are text. And we input lab results. Those of them didn't have it with a reference number. We had to remove 28% of our data set because of missing value. So as you can see, the accuracy is between 70 to 75%. Then we performed two sets of experiment using LLM, one of them using all of the features, and another one is using GPT-4 for feature selection. As you can see, generally LLMs outperform traditional machine learning models, and using GPT-4 and also reducing the space of input can increase the accuracy by 5%. It shows that LLMs not only can model the unstructured data, it also can give us more information and insight of the input and feature selection. Also, there are some limitations. One of the biggest limitation of this study, this was a single center retrospective study just conducted on UC Davis Hospital. And also it was imbalanced data set because only 28% of our data are labeled as ORD. And we didn't address the real-time monitoring and privacy and privacy of the model. So for the future, we are going to evaluate our model in multi-institutional center. And then also we are going to provide an integration of our model with existing system. This is the first study using LLMs for ORD prediction. And also the result shows that how GPT-4 can improve the accuracy with the feature selection. And generally LLMs outperform traditional models in processing clinical narratives. And this is a promising step towards safer AI-assisted opioid administration in hospital. And even if we can integrate it with EMR, we can identify those patients at risk, and we can provide other cares and others. Thank you.
Okay, our fifth speaker, Shuangquan Wang, title is Towards Recognizing Food Types for Unseen Subjects.
Okay, so good morning, everyone. I'm glad to present our paper. The title is Towards Recognizing Food Types for Unseen Subjects. So every day we eat a different kind of food, and each kind of food provides us different nutritions, such as protein, fight vitamins, right? And this nutrition support our health. And so for this paper, we try to automatically recognize the food types from chewing singulars. In our previous study, we use embedded sensors in our headband to detect the skull vibration and the muscle bulge so that we can infer the food types. So this is continued work. And so in order to recognize the food type, normally we will collect data for each person and to build a personalized model so that we can use this model to detect the accuracy of the food types. For some existing work, the accuracy is about, for example, 8% or 85%. However, if we use the trained model for an unknown person, for the person we do not have the training data, the accuracy for existing work is very low, 20% or 25%. And so the question here is that whether we can recognize the food types for unknown user if we do not have the training data for them. And so this should be a research task about the domain adaptation. So when we have the training data for the source domain, means the people we have the label, we have the data distribution in the feature space. However, but for the testing people, the data distribution are different in the feature space. If we use the model does not match for the data distribution. So that's why the accuracy is very low. In addition to that, the sensor deployment and the user eating behavior and performance are totally different. So this gives us a lot of challenge to deal with this task. And for this paper, we try to say, hey, for this domain adaptation task, we know that is there any existing work we can use to deal with this question? And so before we propose our own solution, we test the dataset on some existing work. And we know the upper bound is that we use existing target domain data to train and test in the same domain. That's upper bound for us. And we also try to use existing model to say, hey, what's the domain adaptation accuracy? We tried the 4 different models. For TC and Coral, these 2 models use hand-card features. And another 2 models, Codex and STM, we use model extract features such as deep learning, right? We found that the first observation that the hand-card feature sometimes is better than model extract features. This meaning because for the hand-card feature, sometimes include our domain knowledge. We embed our domain knowledge during the feature extraction process. The second observation is that there are 2 possible ways to do this. First way, we just combine all the source data together to train one model. The second is that we train a model for each person from the training source. Then we use ensemble learning to combine them together. And we found that based on our experiment results, the ensemble learning is better compared with just one model. This is our second observation. In addition to that, if we have another person in the domain, source domain, how much person we should use? All of them or just some of them? And we do some experiment, found that we have, for example, 14 people in the source domain. And so if we have 7 people, the accuracy is the highest. If we have less than 7 people, the data do not fully use. But if we have more than 7 people, the data has much more divergence, and so the accuracy drop. So this existing work do not solve the problem, but give us some potential solution and or guidance. So here, we would like to answer these 3 questions based on the 3 above observations. First one, how to adapt the hand-card features on the domain shift. Second, how to reduce divergence across multiple source domains. Third, how to identify the optimal source domain for transfer. To answer the question, we propose such following pipeline. First one, based on the hand-card features, we propose a stratified normalization. This can deal with the data divergence in the feature space. This is more like the data adaptation. In addition to that, followed by this process, we propose a multi-source domain adapter. In this module, we first pass all the data through the shared layers to extract some robust features. And after that, we design a domain-specific adapter for each source domain. And first, we will try to build a mapping relationship from the feature to the label based on the training data using cross-entropy loss. In addition to that, we also use the data from the target domain and use maximum mean discrepancy to learn or to reduce the source target divergence. We will do this for all the source from the source domain. But in addition to that, there is one thing we do not deal with. From the multiple source, the source distribution also different. So we also propose another module called a consensus regularizer. This module is special to deal with or reduce the source divergence. Then based on the MMD and the CR module output, we can make a decision of all the source domain, which source we should select. And for each source, what's the weight for them, and we just combine them together for the model. And for the first one, stratified normalization, in fact, it's very simple. Normally, when we try to normalize data, we just combine all the data together. However, this cannot align the source domain and the target domain very well. In addition to do that, instead of do that, we will try to normalize data for each source separately, and we first do normalization and then combine them together. So this can help us to align the data from the source domain and the target domain very well. So the key insight here is the chewing behavior varies across users, but the food characters remain consistent. For the consensus regularization, we know we use MMD to deal with the source target divergence, but we will use CR to deal with the source divergence. So here, the right side figure shows the training accuracy and testing accuracy. Before we use CR, we found that their training testing accuracy, there is a big gap. However, if we include CR, this gap is much smaller. And so this smaller part comes from the benefits of the generation ability. So we can say that the CR can help us to reduce the overfitting and improve the model generalization ability. So key insight here is that divergence among source domain maybe impact the generalization ability, but motivate us to deal with the source alignment. The third part, if we have multiple source domain, which one we should keep and which one is more important? So here, the insight is we try to select the most informative source domains and only assign the weights based on their similarity. We propose a threshold-based method. If the entropy is less than threshold, we do not keep it. We only keep the source domain with the above the threshold. And for each source domain, we will based on the similarity. We will give higher weights to the source domain, which are similar with the target domain. So in this case, we just combine all the source domain together to build a model. The right side figure shows the relationship between the threshold and the number of the source domain. We can say that with the increase of the threshold, the number of source domain decrease. That's trainable. And the dotted line shows the relationship between the threshold and the accuracy improvement. We can say that in the middle, for example, when the threshold is about 0.7 or 0.75, we have the highest accuracy improvement. At that time, we maybe only use 6 or 7 source domain. This is the same as we observed above, right? But one thing is that based on the figure, we can say no matter what's the threshold, the accuracy improvement is always positive. That means for our method, we never worse the classification performance. So in order to evaluate our method, so we compare our method with 9 existing baseline. And so for the comparison, our method not only deal with the data adaptation, but also for the model adaptation. We not only deal with the source to target divergence, but we also deal with the source divergence. And for the ensemble learning, we not only select the most important source domain, but also we give the weights for different source. And we use leave one user out cross-validation method to evaluate our method. This figure shows the overall performance. The upper bound is the training and testing on the target domain. The lower bound is training on the source domain, use estimate and testing on the target domain. And we found that for TC and Coral, these two methods does not support multi-source adaptation. The performance is low, that's reasonable. And for some other methods, they do not address source divergency. Their performance is also very low. And our performance on every number of sources are always, compared with all the other methods, always the best. And even there are two methods which also deal with source divergency, but our method is still higher than them, more than 10% accuracy. So this just shows the performance of our method. Another thing that we propose a pipeline contain multiple modules. We would like to say, hey, for each module, what's the contribution to the accuracy? We just decompose them. We found that if we include S-norm, we will increase accuracy for line 7%. And if we include ensemble, we increase 2.8%. MSD adapter, 4.7, CR, 6.9, and weighted representative, 1%. Combine all them together, we improve more than 20% accuracy compared with the, without our method. Also, the S-norm method, we can improve accuracy with or without ensemble. It's better, right? And our MSD adapter is better than the sequential structures. So another question is that if we have the training data from a source domain, but we do not have a label for all the data, just have partial label, what happened for that case? We also do an experiment to evaluate. For the data source, for each source, we only have partial labels from 33% to 100%. We found that no matter for which percent, our method is always outperform for any of the existing baseline. And so this shows even with limited label for the source domain, we can also use our method to have a better performance. Just to conclude, we propose a pipeline to deal with the domain adaptation. We not only deal with the data adaptation, but also for the model adaptation. We not only deal with the source target divergence, but also we deal with the source divergence. And so we just use food type recognition as one example. But I believe this method can also use for any other domain adaptation method. And so finally, I'd like to just give the credit for the first author. The first author prepared all the slides, but he cannot join us. But anyway, we are very glad to answer any question you may have. Thank you.